వచ్చిందా? So friends, good evening. How many of them? So 40 of you have assembled as of now. Can I wait for some time for the people to come, or is it going to be this trend? I don't know. I cannot ask you because you cannot respond to me. Now at the beginning, let me go through your doubts. Continue in English, sir. I will try to. What is critical radius, sir? I think this question more than twice I have this concept I have explained to you. Critical radius of insulation is that radius of insulation when put on a radial surface, maybe pipe or a sphere, initially enhance the heat transfer and finally reaches a maximum at some point, and thereafter any further addition of insulation will result in reduced heat transfer. Heat transfer starts decreasing from there. Meaning what? There is a bare pipe, some heat is lost into the surroundings from the bare pipe because of convection heat transfer. Now you started adding insulation. You go on increasing the thickness of insulation, meaning you are increasing the outer radius of the insulation. And when you initially start adding the insulation, the effect is to increase the heat transfer. I told you the reason. One is there are two resistances coming in path: conduction resistance through the insulation material and convection on the top of it. Because the insulation area is increasing, when insulation thickness is increasing, outer area increases and therefore convection heat transfer increases or convection resistance decreases. So one resistance is increasing, another resistance is decreasing, and initially the reduction in convection resistance is more than increase in conduction resistance, and therefore effectively resistance decreases and heat transfer increases. It goes on, reaches a maximum, and the radius corresponding to where the maximum heat transfer takes place is critical radius of insulation. Beyond that, if you go on adding insulation beyond critical radius of insulation, heat transfer decreases. And what is critical radius of insulation? The mathematical expressions I have given it to you. For a cylinder, it is K by H. You need to remember that. For a sphere, it is 2K by H, where K corresponds to thermal conductivity of the insulating material. H corresponds to the heat transfer coefficient between the insulation and the surroundings. So I don't think I need to explain it anyway better. Now, one student asked me, if you say you take a hollow pipe, maybe for you, I'll just right. Okay. Let me say this is the pipe, and on top of it you are adding insulation. I said this is insulation. Now we have talked about the resistance, conduction resistance through the insulation, and the convection resistance outside the insulation. Okay. Now here I said this is outside. This is the pipe. This is the pipe. This thickness, where my finger is, filling the gap, is the thickness of the pipe, metal pipe, let me say. On top of it, you have added insulation. So when you add insulation, I am talking about outside insulation, as we have discussed it, critical radius of insulation. When you add it outside, conduction resistance increases, conduction resistance, it increases, convection resistance decreases because increase in area. Now, the question asked by the student is, if you have a pipe like this, and what if you add insulation Now the hatched portion, I'm talking about insulation inside the pipe. Maybe some fluid is flowing through this. Okay, let me say some fluid is flowing through this pipe. You add insulation internally. Now when you add insulation internally inside the tube, inside the pipe, the critical radiation will not apply at all. Why? Now heat transfer should happen this way, radially inward. And now insulation is the first layer, metal is the second layer. Now because of the thickness of insulation, conduction resistance increases. Now there are two resistances. One is the conduction resistance through the insulator, conduction, and convection resistance. The second is between the fluid and the insulation pipe. So it is convection resistance. What is convection resistance? It is 1 by HA. Okay, heat transfer coefficient, let me say it is constant, it's not varying. Now what is happening when you're going for inside insulation, if you increase the thickness of insulation, the inner radius decreases. That's because it shrinks. Inner radius decreases. When inner radius decreases, area decreases. What is area? 2 pi r into L. So if you go on adding insulation towards inside, maybe look at the arrow. Look at the arrow. If you are going, if you are continuously increasing the insulation towards inside, the radius goes on reducing, and therefore area reduces. So convection resistance, what happens? 1 by HA. So when area reduces in the denominator, convection resistance also increases. Now, when you are adding insulation towards the inside of the pipe, both resistance increase. When both resistance increase, obviously heat transfer is reducing. So internally, inside a pipe, if you go on adding, if you have a pipe like this, if you start adding insulation inside it like this, now the effect is only to reduce the heat transfer. Heat transfer cannot initially increase and then decrease. That happens when you add insulation outside the pipe. Whereas here, what is happening? Both the resistances, because you are adding insulation inside, the conduction resistance, increases. Resistance is added into it. Lagging happens there. And convection resistance, if you go on adding, the radius continuously decrease, and therefore the area decrease. Even convection resistance also increase. Both the resistance increase, and therefore you cannot have the concept of critical radius of insulation there. It is only going to lead to reduced heat transfers when you are insulating inside the pipe. Am I clear with this? So the two cases. That's an intelligent question. That's a good question asked by a student. Now, what happens when you add insulation outside? What happens when you add insulation outside? When you add insulation inside, the heat transfer continuously reduces because of the addition of insulation, because both the resistances increase. When you add it outside, conduction resistance increase and convection resistance decrease by virtue of the increased surface area. So, therefore, the critical radius applies only when you add insulation outside. Okay. Now, one student asked, the conditions for first and second type of fin seems to be the same. No, they are not the same. The T minus T infinity. What is T? T is the temperature of the fin at any given X value. X is varying at whatever X value you are talking about. What is the temperature of the fin? That is T. And T infinity is the ambient temperature. Always we are talking about temperature difference between fin and ambient temperature. So therefore theta becomes 0 here. Am I right? Theta becomes 0 here. Right. And the second condition is about, adiabatic fin. Negligible heat loss at the tip. That means what? You are insulating this tip. And this means what? The fin is not very long fin. It's a short fin only. The temperature at this point cannot be equal to T infinity. It is still higher than T infinity. So at that condition, when you insulate abruptly, you insulate the tip of the fin, no heat transfer takes place, and therefore I assume a condition, or from the boundary conditions what we know, at an insulated condition, when it is perfectly insulated, dt by dx is equal to 0. So that means d theta by dx is also 0 at the fin. So no confusion between the first and second case. In the first case, the tip of the fin has already reached the ambient temperature, and therefore theta becomes 0 at x equal to L. Whereas in this case, T is not equal to ambient temperature at the tip of the fin, whereas heat transfer is not taking place at the tip of the fin because it is insulated. So the boundary conditions change. The governing equation is the same. Now the governing equation is this. Theta x is equal to, the solution is this. Theta is equal to C1 e to the power of x plus C2 e to the power of minus mx. So this continues. Okay. And in the third condition, fin tip, why the convection not happening when there is a temperature difference? What is the third condition? Third condition is, I said, known temperature at the tip. No, convection is happening at the tip, but I measured this temperature. This temperature is measured to be TL, meaning I know the temperature there. When someone is measuring the temperature, indicate that the temperature at the tip is TL, I take that as a boundary condition. Convection is still happening, but I take TL as the temperature, the condition, and assume that the TL is not changing. Then my solution is quite simple because I have two definite boundary conditions. One is at x equal to 0, theta is equal to T naught minus T infinity, TB minus T infinity. At x equal to L, it is TL, known temperature. Unknown temperature, you cannot use it. Someone measured this and said that the temperature at the tip is TL. I straight away use that, and theta at x equal to L is TL minus T infinity. And okay. When we place a cylinder tangentially to the plate, how to study the heat transfer to such fins are? Cross-section area will be varying continuously. I said there are two types of fins. One is a constant cross-section area of the fin. Another one is a varying cross-section of the fin, like a triangular fin attached to it. So the approach is altogether different. We are not solving for the problems of varying area. We are just solving the problems of constant cross-sectional area. In fact, I have shown you a derivation for the varying area. So don't get confused. Both are possible. Varying area fin is possible, and constant cross-sectional area is also effective, and is also possible. And this gentleman asked me to teach in Telugu. I don't know which language should I switch on. Okay. So someone asked me to give questions without answers so that you can practice on your own. Maybe I'll try it. Okay. Okay. And one final question, I'll take it. What conditions the fin effectiveness and efficiency are equal? See, this is another question asked. See, you cannot compare. Fin efficiency is the ratio of efficiency of the fin is the ratio of the actual heat transfer taking place in the fin divided by maximum possible heat transfer that can happen through a fin. I explained what is efficiency. Efficiency is and someone, if you have not understood my explanation, let me explain it in Telugu. Let me initially explain it in English, so that I'll satisfy both of you. Both requirements. Now, if you have a film, it is transferring Q amount of heat because of the presence of the fin. And if this fin is replaced with a zero resistance fin material, maybe very, very, very high thermal conductivity fin or zero resistance, so that entire fin is maintained at its base temperature. That's an ideal condition. I said practically it is not possible. Ideally, it is possible. Ideally, you can imagine when you say RTH is 0, I have drawn the temperature profile. Temperature profile is horizontal along the x direction. It is not going to drop. Such a condition, what is the heat transfer that may happen? That is the maximum heat that can happen. So, whether like your Carnot efficiency, like any heat engine you are talking about, heat engine will have certain efficiency. Then we all know that Carnot cycle will have the maximum efficiency operating between the same temperature limit. Carnot cycle will have the maximum efficiency operating under the same temperature limits as compared to any other cycle. But we all know that Carnot cycle is not a practical cycle. Why? Because you have two reversible adiabatics and two reversible isotherms. Isothermal process needs very slow process. Reversible adiabatic needs very fast movement of the piston. So it is not possible for you to have. Sorry, there is some disturbance. I think I should. వాళ్ళు మాట్లాడుతున్నారు. Sorry for the disturbance. Some noise coming in between. I am trying to set it right. I'm sorry. Okay. Obvious. It has been corrected. Okay. So a Carnot cycle is not practical cycle because you imagine half of a revolution it runs fast, half of a revolution it runs slow. It is not going to be possible. But still, we use Carnot cycle because Carnot is the heat transfer that is taking place at the area of the base. Heat transfer with fin is any of these equations depending on the fin condition. So you can calculate. Effectiveness of the fin ఎంత చెప్పాను నార్మల్గా 40లో ఉంటాయి చెప్పాను. It ranges to 40. And 40 means what? Without a fin, some Q heat transfer is taking place. If you use a fin, 40 times Q will happen through the fin. So that is the advantage of fin. Okay, right. Thank you. So we cannot compare both of them. So could you please guide us in order to crack GATE, IES, what source are to be required to cover to clear IES and GATE examination? What is required for you to crack GATE and IES is a strong commitment. Now we are giving these coachings and all. So if you are not taking me very serious, if you are not taking it that way that I am pulling your leg, let me tell you. Prior to 2000, there was no such coaching centers, there was no such GATE training by the professors exclusively. Students, parallelly they started preparing for the subject as well as the GATE examination. They always had GATE questions and possible GATE questions while preparing for the examinations of the university. They also prepared parallelly for the possible questions that are asked in GATE. And it was a continuous effort from first year till final year. Now, if you're looking at a shortcut solution that you're not serious in your classroom, and all of a sudden you wanted all shortcut methods to be taught to you, and you just wanted with minimum effort you wanted to crack these examinations, it's not going to be possible. See, it is like this. I told you, once almost 1.5-2 decades back, there are plenty of Andhra students from Andhra Pradesh, engineering colleges, very effortlessly cracking GATE and IES examinations. Now, the number is quite minimum. That obviously means you are not really focused in your classrooms, or the way you are preparing for the subject, the way you are acquiring the fundamental concepts of the subject needs a little more focus. And for some reason, maybe IT jobs started coming to you very easily, and therefore you stopped, working hard on your subject. Maybe I just thought, I'm just thinking louder. maybe you can think for yourself where it is going wrong. జరుగుతుంది. Why do you need, say, separate coaching when you are very attentive to your classroom, when you are following a very good textbook, and today you are supplemented with a lot of e-learning resources from NPTEL, etc. There are plenty of e-learning resources, open sourceware of you can even go through the lecture notes of Massachusetts or Stanford University professor or IIT professor straight away. So the the subject knowledge is available, and there are many ways you can acquire the knowledge, but you need to be a little more focused. If you are not misunderstanding me, I'm just reminded of a small poem in Telugu. మీకు అందరికీ బృందావనం తెలుసు కదా, మధురలో ఉంటుంది బృందావనం. ఆ బృందావనం అంటే లార్డ్ కృష్ణ ఉన్న బృందావనం. బృందావనం అంటే మనకంతా బ్యూటిఫుల్ ప్లేస్ అని అనుకుంటాం కదా. చామర్తి రాజశేఖర్ గారని ఒక కవి ఆ బృందావనంకి వెళ్తాడు. మీరు కూడా ఎప్పుడైనా వెళ్తే చూడొచ్చు. ఇప్పుడేం ఉండవు అక్కడ, అంత బ్యూటీ ఏమి ఉండదు, అంత తుప్పలు చెట్లు ఉంటాయి. సో అవి చూసిన తర్వాత ఆయన ఇట్లా రాస్తాడు. ఆ యమునా నది పరిసరాగత మంద సమీర వార మేచాయల పోయినం, దశ దిశావృత తుంగ తురంగ మాలిక తోయకనంబు లేఖడల అరతించను, మాయురే రమ్య వస్తు చేయమంతయు కృష్ణుడి వెంటనంటేనే. అంటే అవన్నీ ఆ బ్యూటీ, ఆ ప్లేస్ యొక్క బ్యూటీ అంతా ఎక్కడికి వెళ్ళిపోయిందో, ఆ గ్లోరిఫికేషన్ అంతా ఎక్కడికి వెళ్ళిపోయిందో అంతా కృష్ణుడితో పాటు వెళ్ళిపోయిందా. సో మళ్ళీ ఇప్పుడు you all needed to rebuild this Vrindavan. This Vrindavan is all about focusing on your skill, also focusing on your domain knowledge. Sorry, so I just don't want to tell you more. It's not such a great job, but also let me tell you, having said that, if you think by just preparing for a month to crack IES and GATE examinations, I don't think you can be comfortable cracking them. So you need to have a continuous effort right from second year. Those, I'm sure my audience are third year and fourth year. Fine, you can start preparing from now on. And because GATE comes next February. Next February, still there is a lot of time. You can very systematically go through. But there is no shortcut for this. Don't depend on formulae, by hearting and reproducing, recollecting. You need to work on the problems. You need to work on the concepts. So first understand the concept, and slowly any complicated problem can be solved. Right, my dear friends? And I think we have discussed about everything what we needed to discuss about the fins and unsteady state. There is one concept I could not complete in unsteady state. That is the time constant of a thermocouple. So let me explain this and then move further. What is time constant of a thermocouple? Now, why do you use a thermocouple? Thermocouple is used to measure the temperature of a fluid. Now, if the temperature of fluid, like if your thermocouple purpose is to measure temperature of a fluid in a tumbler, in a glass kept here, in a vessel, water kept in a vessel, the temperature is not very dynamic, it's not changing, and thermocouple can record its temperature correct. Whereas, let me say I want to measure the temperature of the gases inside the IC engine cylinder. When I want to measure the temperature of the gas inside the IC engine cylinder, during suction stroke, the crankshaft rotates at around 3000 RPM. Meaning what? 3000 revolutions per every minute. So per second, how many of them? Close to 500. Every second 500 times, the shaft rotates. That means what? 500 times you have 2 strokes. That means 1000 strokes happen. And in a given second, 1000 strokes happen. The piston is so fast moving up and down, the temperatures are continuously changing. You insert a thermocouple into it, and if thermocouple is not reaching the ambient temperature, if the thermocouple is not reaching the ambient temperature, The thermocouple principle is Seebeck effect. When two dissimilar metals forming into two junctions and an EMF is induced into it, EMF can be calibrated to record the temperature. That is the principle by which it works. Now, how is this EMF induced in the circuit when two, not all two metals can give, only certain combinations can work well for the Seebeck effect. Okay, certain combinations you chose two dissimilar metals formed into two junctions. Now, EMF induced in the circuit depends on the temperature difference between the hot and the cold junction. Hot junction and cold junction. Now, this hot junction is the junction, let me say, is the junction where the point where which is actually sensing the temperature of the fluid, which you have measured. Now, the fluid temperature is continuously changing. By the time it realizes the fluid temperature, probably actual temperature would have changed because, in a second, 1,000 times. Now, how do you say now my thermocouple gave me temperature of 300 degrees centigrade or 500 degrees centigrade. Where did it give? Is it at the end of a section stroke or middle of section stroke or middle of compression stroke? With respect to time, when I see the dynamics of the fluid temperature change should be, adapted by the thermocouple. Thermocouple also shall be changing the temperature at its tip. Otherwise, measurements are erratic. So, the dynamic response of a thermocouple can be analyzed using this, what you call unsteady state heat transfer. Now, the lumped heat capacity analysis. What did I say? The lumped body, when it is dropped into an environment, I said T minus T infinity divided by Ti minus T infinity is equal to e to the power of minus, Biot number, Fourier's number, isn't it? Is it? So it is an exponential variation. I said when you take temperature on y-axis, time on x-axis, let me say the initial temperature is Ti, and when time t is equal to 0, it is the initial temperature. When you drop into a new environment of lower temperature, let me say the ambient temperature is T infinity, because the temperature variation is an exponential function. The temperature is exponentially decreasing, and it is asymptotic with x-axis that it moves very close to the x-axis, but it meets only at the infinity. That is the exponential function. But majority of the temperature drop would have occurred in a limited time, but thereafter the fluid and the lumped body, both it takes a long time for both the temperatures to become equal. That's what exponential variation of temperature means. So at least you cannot wait infinitely long time. That's what I said. My problem is I should be using a thermocouple to measure very dynamic situations. Fluid, constant fluid temperature, it's fine. Like measuring your body temperature, measuring water temperature in a glass, it is not varying much. Whereas measuring the temperature of engine cylinder, suction stroke, right from TDC to PDC, it is changing. And again, compression stroke from PDC to TDC, it is changing. Because it is compressing, it is heating up, and all of a sudden you are firing the fuel, you are burning the fuel, be it CI or SI, and heat is released, enormous heat is released, temperature surges very drastically, and pressure is increased, pushes the piston down. So every stroke temperature is varying. How much time it is taken for a stroke? Hot of few milliseconds, not more than that. So every time when the temperature is changing, your thermocouple, initial temperature is Ti. What do you mean by initial temperature? Now when your piston and cylinder are this, here now it has one temperature. It has one temperature, let me say Ti. Now the piston changed. Now the thermocouple is here. It is now exposed to a new environmental temperature T infinity, because piston is displaced, temperature varies. So immediately it should adapt to the environment temperature. So how much time? Is it instantaneous? Is it like a vertical line? No, it is not a vertical line. It is only an exponential function. It takes some time. So people, when they design a thermocouple, now based on the temperature difference, initial temperature difference between The thermocouple and the ambient condition is Ti minus T infinity. Ti minus T infinity. Ti minus T, initial temp. What I mean, I have a fluid there, it is at 100 degrees centigrade. I have a thermocouple, now it is 30 degrees centigrade. So temperature difference between thermocouple and fluid is 30 minus 100. Okay, minus 70 degrees centigrade. That is the initial temperature. The moment I introduce the thermocouple into the fluid, the thermocouple shall reach the fluid temperature immediately. Because immediately your digital display is giving the thermocouple temperature recorded by thermocouple. Now, by the time it indicated the temperature, this thermocouple, question is this, whether this thermocouple has reached the fluid temperature. Fluid temperature ఎంత అన్నాను 100 degrees centigrade అన్నాను. థర్మోకపుల్ ఇనిషియల్ గా ఎంత ఉంది 30 degrees. 30 degrees థర్మోకపుల్ టెంపరేచర్ ని నేను అక్కడ ఇంట్రడ్యూస్ చేస్తానే ఓ 2 seconds తర్వాత అది 60 degrees వచ్చిందా 70 degrees వచ్చిందా నాకు తెలియదు. అది 70 degrees చూపిస్తే నేను ఫ్లూయిడ్ టెంపరేచర్ కూడా 70 degrees అని చెప్తాను. ఈ డిజిటల్ డిస్ప్లే ఏం చూపిస్తుంది, థర్మోకపుల్ ఎంత టెంపరేచర్ రికార్డ్ చేస్తుందో, ఎంత టెంపరేచర్ లో ఉందో థర్మోకపుల్ టిప్, వాట్ ఈస్ ద టెంపరేచర్ అక్వైర్డ్ బై ద థర్మోకపుల్, దానికి కరెస్పాండెంట్ గానే, బికాస్ సీబెక్ ఎఫెక్ట్ ఈస్ ఆల్ అబౌట్ ఈఎంఎఫ్ ఇండ్యూస్డ్. ఈఎంఎఫ్ ఇండ్యూస్డ్ ఈస్ బేస్డ్ ఆన్ ది హాట్ జంక్షన్ టెంపరేచర్, రైట్? సో థర్మోకపుల్ ఎంత టెంపరేచర్ ని అక్వైర్ చేసుకుందో దానికి తగిన టెంపరేచర్ డిస్ప్లేనే అక్కడ వస్తుంది. ఇక్కడ ఇష్యూ ఏంటి, థర్మోకపుల్ టెంపరేచర్ ఫ్లూయిడ్ టెంపరేచర్ సేమేనా, అవి రెండు ఈక్విలిబ్రియంకి వచ్చాయా? అండ్ ఎప్పుడు వస్తాయి ఈక్విలిబ్రియంకి? టైం చూడండి, దిస్ ఇస్ ద టైమ్ ఆన్ ఎక్స్ యాక్సిస్. ఇట్ టేక్స్ ఇన్ఫైనైట్లీ లాంగ్ టైమ్, whereas in the initial part the maximum temperature difference is covered in a short time, but exactly going there, to equilibrium, it takes a very long time. Now ఎంతసేపు వెయిట్ చేయాలి నేను థర్మోకపుల్ డిజైన్ చేసినప్పుడు? వాట్ ఈస్ అ గుడ్ థర్మోకపుల్? For example, I have a thermocouple. I'm sorry, I'm taking too long time on this, but then let me try this concept. I have a thermocouple made of, say, iron constant in. Okay, I have another thermocouple, copper constant combination. Two dissimilar metals, kada? So iron constant in పెట్టినప్పుడు, let me say 100 degrees లో పెట్టేదానికి 100 degrees water లో when I dip it, now let me say it is taking long time, say 5 seconds 10 seconds తర్వాత కానీ fluid temperature reach కాలేదు. కాపర్ కాన్స్టాంట్ తీసుకున్నాను, కాపర్ కాన్స్టాంట్ నేను ఇన్సర్ట్ చేస్తాను, 2 seconds లోనే ఫ్లూయిడ్ టెంపరేచర్ రీచ్ అయిపోయింది. విచ్ ఇస్ ద బెటర్ థర్మోకపుల్ ఫర్ మీ? కాపర్ కాన్స్టాంట్. ఎందుకు? చాలా క్విక్ గా ఎన్విరాన్మెంట్ టెంపరేచర్ కి అడాప్ట్ అయిపోతుంది. అంటే ఇనిషియల్ డిఫరెన్స్ ఏదైతే ఉందో టిఐ మైనస్ టీ ఇన్ఫినిటీ, ఇనిషియల్ గా థర్మోకపుల్ ఏ టెంపరేచర్ లో ఉంది, ఇనిషియల్ గా ఫ్లూయిడ్ ఏ టెంపరేచర్ లో ఉంది. దాన్ని ఇంట్రడ్యూస్ చేసినప్పటి నుంచి టైం స్టార్ట్స్ మూవింగ్ కదా, ఎంత క్విక్ గా అది అంబియంట్ ఫ్లూయిడ్ టెంపరేచర్ వచ్చేస్తుంది. దీన్ని బేస్ చేసుకొని టైం కాన్స్టెంట్ డిఫైన్ చేస్తారు. వాట్ ఈస్ ద టైం కాన్స్టెంట్ ఆఫ్ ఎ థర్మోకపుల్? ఇట్ ఈస్ ది టైం రిక్వైర్డ్, to reduce the initial temperature difference by 63.2%. అంటే ఏంటి? ఇందాక టెంపరేచర్ డిఫరెన్స్ ఏమన్నాను ఎగ్జాంపుల్లో, టిఐ 30 అన్నాను, టీ ఇన్ఫినిటీ 100 అన్నాను, టెంపరేచర్ డిఫరెన్స్ 70. ఇనిషియల్ టెంపరేచర్ డిఫరెన్స్, దట్ ఈస్ థీటా ఐ. డినామినేటర్ లో ఇక్కడ మీకు కనిపిస్తుంది కదా స్లైడ్ లో, థీటా ఐ ఈజ్ 70 మన ఎగ్జాంపుల్ లో. థీటా ఐ అంటే ఇనిషియల్ టెంపరేచర్. నా ఇప్పుడు ప్రజెంట్ టెంపరేచర్ డిఫరెన్స్ అంటే కొంత టైం తర్వాత ఎంత ఉంది టెంపరేచర్ డిఫరెన్స్. ఈ టైం కాన్స్టెంట్ ఏం చెప్తుందంటే, ఇట్ ఈస్ ద టైం రిక్వైర్డ్ ఫర్ ద థర్మోకపుల్ టు రెడ్యూస్ ద ఇనిషియల్ టెంపరేచర్ డివైడ్ బై 63.2%. అంటే 70 degrees centigrade డిఫరెన్స్ ఉన్నది, 63.2% తక్కువ అయిపోతే ఎంత డిఫరెన్స్ ఉంటుందో ఆ డిఫరెన్స్ రావడానికి, అంటే 63.2% రెడ్యూస్ అయిందంటే ఎంత పర్సెంటేజ్ ఉండాలి? ఇంకా 36.8%. సో 70 into 36.368 ఎంత టెంపరేచర్ వస్తే అంత టెంపరేచర్ డిఫరెన్స్ రావడానికి ఎంత టైం పడుతుందో దాన్ని మనం టైం కాన్స్టెంట్ అంటే ఇక్కడ మళ్ళీ చెప్పాను. ఒక టైం కాన్స్టెంట్ ఆఫ్ థర్మోకపుల్ ఎక్కువ టైం తీసుకుంటుంది టు రీచ్ ఇట్స్ ambient టెంపరేచర్ ఆర్ ఫ్లూయిడ్ టెంపరేచర్, ఎన్విరాన్మెంట్ టెంపరేచర్. ఇంకో థర్మోకపుల్ కి మోడరేట్ టైం తీసుకుంటుంది, ఇంకో థర్మోకపుల్ కి చాలా తక్కువ టైం తీసుకుంటుంది. నేనేమంటున్నాను, T3 is a better thermocouple to record the dynamic response of the fluid temperature change of the environment. అంటే దీని టైం కాన్స్టెంట్ బాగా తక్కువ. సో టైం కాన్స్టెంట్ ఆఫ్ థర్మోకపుల్ ఏమంటానంటే, by definition it is this: the time required for the thermocouple to reduce the initial temperature difference by 63.2%. అంటే ఏంటి, ఇనిషియల్ టెంపరేచర్ డిఫరెన్స్ ఇది, థీటా ప్రెసెంట్ టెంపరేచర్ డిఫరెన్స్ ఇది. సో దీంట్లో 63.2% రెడ్యూస్ అయిపోవాలంటే ఇంకెంత మిగిలి ఉండాలి టెంపరేచర్? 36.8. సో థీటా బై థీటా ఐ ఇస్ ఈక్వల్ టు 0.36. ఓకే, సో మనకి ఈక్వేషన్ ఏంటి? ఈక్వేషన్ ఏంటి మనకి? T minus T infinity divided by Ti minus T infinity is equal to e to the power of minus HA divided by rho CPV into T. అంతే కదా, e to the power of minus HAT divided by rho CP by V. ఇదేమన్నాను థీటా, ఇదేమన్నాను థీటా ఐ. సో టైం కాన్స్టెంట్ వచ్చేసరికి థీటా బై థీటా ఐ ఇస్ ఈక్వల్ టు 0.368 ఉండాలి, అంతేనా? 0.368 ఉండాలి. దట్స్ ఈక్వల్ టు థీటా బై థీటా ఐ ఇస్ ఈక్వల్ టు 0.368 e to the power of minus HA divided by rho CPV into T. రైట్. సో ఇక్కడ నేనేం చెప్తానంటే, I'm sorry, can I use a fresh thing? Okay, I'm sorry. ఇక్కడ ఏమంటానంటే 0.368 ఈజ్ ఈక్వల్ టు థీటా బై థీటా ఐ, టైం కాన్స్టెంట్ కండిషన్ అప్లై చేస్తున్నాను, e to the power of minus HAT divided by rho CPV కదా. సో 0.368 ఏంటంటే e to the power of minus 1. e to the power of minus 1 is equal to 0.368. You can even operate your calculator and say check it. So it is HAT divided by rho CP. Okay, so that means what? HAT divided by rho CPV is equal to 1. T star అంటాం దీన్ని. T star is equal to rho CPV divided by HA. ఇది టైం కాన్స్టెంట్ ఆఫ్ ఎ థర్మోకపుల్. సో థర్మోకపుల్ టైం కాన్స్టెంట్ ని, అది దాని ఫిజికల్ పారామీటర్స్, ఏరియా, సర్ఫేస్ ఏరియా ఆఫ్ ది థర్మోకపుల్, వాల్యూమ్ ఆఫ్ ద థర్మోకపుల్, థర్మోకపుల్ టిప్ యొక్క స్పెసిఫిక్ హీట్, థర్మోకపుల్ టిప్ యొక్క డెన్సిటీ, వాట్ ఈస్ ద హీట్ ట్రాన్స్ఫర్ కోఎఫిషియంట్ అసోసియేటెడ్ విత్ దట్, ఇవన్నీ బేస్ చేసుకుని టైం కాన్స్టెంట్ ని తీసుకుంటారు. సో వెన్ యూ గో అండ్ పర్చేస్ ద థర్మోకపుల్, నువ్వు టైం కాన్స్టెంట్ తక్కువ ఉన్న థర్మోకపుల్ ని తీసుకుంటావు. ఇట్స్ యాజ్ సింపుల్ యాజ్ దిస్. This helps you in understand. Okay. Now, I think I have explained almost every concept in conduction. Very quickly, if time permits, let me go through some of the problems. Okay, I mean quiz problems. So very quickly, and ఇందాక మనం డిస్కస్ చేసుకున్న అన్ని ఆస్పెక్ట్స్ మీద, the value of Bayes number is very small, less than 0.01, maybe very small. When is it? Bayes number అంటే ఏమన్నాను నేను? Bayes number is the ratio of internal resistance to external resistance. నిన్న అప్పటికే సాచురేట్ అయి వినలేకపోయిన వాళ్ళకి చెప్తాను. ఇది లంపుడ్ బాడీ అనుకుందాం. లంపుడ్ బాడీ ఏంటంటే ఇది సాలిడ్. సో దీనికి కండక్షన్ ఇన్సైడ్ జరిగిందంటే దానికి రెసిస్టెన్స్ ఉంటుంది కదా, ఎందుకంటే సాలిడ్ కదా ఇది కండక్షన్ రెసిస్టెన్స్. ఓకే, అండ్ ఇక్కడ కన్వెక్షన్ రెసిస్టెన్స్ జరుగుతుంది బయట, ఎందుకంటే బయట ఫ్లూయిడ్ ఉంది, దానికి హెచ్ ఉంది, దాని టెంపరేచర్ T ఉంది. సో దేర్ఫోర్ there is one more resistance, heat transfer flow path lo idi solid to environment kaavachu, environment to solid kaavachu, whichever way. So there is conduction and convection resistances. Now Bayat number em cheptundi, Bayat number compares the conduction resistance to convection. Bayat number is equal to HL by K. నేను ఏం చెప్పాను, Bayat number is equal to L by Ka divided by 1 by H. Okay, so A cancel అయిపోతే, so H పైకి వెళ్తే it is HL by K. Where L is characteristic dimension, అది కూడా కన్ఫ్యూజ్ కావద్దండి, L is volume divided by surface area, ఇది కూడా చెప్పాము. ఓకే, సో Bayat number దేన్ని కంపేర్ చేస్తుంది, సాలిడ్ ఇంటర్నల్ రెసిస్టెన్స్ అంటే కండక్షన్ రెసిస్టెన్స్ సాలిడ్ లో ఎంత ఉంది, కన్వెక్షన్ రెసిస్టెన్స్ దాని బయట ఎంత ఉంది. న్యూమరేటర్ లో ఏమో కండక్షన్ రెసిస్టెన్స్, డినామినేటర్ లో ఏమో కన్వెక్షన్ రెసిస్టెన్స్, అంతే కదా. సో ఇది ఏంటి, Bayat number is small one, ఎప్పుడు న్యూమరేటర్ తక్కువగా ఉండాలి, డినామినేటర్ ఎక్కువగా ఉండాలి, అంతే కదా. సో ఏముంది అక్కడ ఆప్షన్స్, కన్వెక్టివ్ రెసిస్టెన్స్ ఆఫ్ ఫ్లూయిడ్ ఇస్ నెగ్లిజిబుల్, conductive resistance of fluid is negligible, conductive resistance of conductive resistance of solid is negligible, none of this. So convective resistance of fluid, external resistance, conductive resistance of fluid, మనం కండక్టివ్ రెసిస్టెన్స్ ఆఫ్ ఫ్లూయిడ్ గురించి మనం ఎక్కడ మాట్లాడట్లేదు, మనం దేని గురించి మాట్లాడుతున్నాం Bayat number లో, we are talking about the conduction resistance inside the solid. When I am talking about conduction resistance inside the solid, the fluid thermal fluid resistance will not come into picture at all. We compare fluid convection resistance and solid conduction resistance. So denominator takkuva unte Bayat number takkuva undadu, A is ruled out. Conductive resistance of fluid gurinchi manam maatladane akkarledu, that is also eliminated. So denominator ఏది, conductive resistance కాబట్టి అది తక్కువ ఉంటే Bayat number. Okay, so ratio of internal conduction resistance to surface convection resistance is known as Kirchhoff number, Bayat number, Stanton number, Prandtl number. Now ఇప్పటి వరకు మీకు Bayat number, Fourier number మాత్రమే చెప్పాను నేను. There are many other numbers that we are going to discuss down the line, and finally when you take the examination all these numbers give you big confusion. So just now we have discussed only Bayat number, you would easily say it is a Bayat number. So internal conduction resistance to surface convection resistance is known as Bayat number. Okay, the other numbers as and when we come across we discuss. Heisler charts are used to determine transient heat flow rate and temperature distribution. అంటే Heisler and Grover charts అని ఉన్నాయి, చార్ట్ సొల్యూషన్స్. అంటే మీరు ఇప్పుడు లంపుడ్ మ్యాథమెటికల్ అనాలిసిస్ కాకుండా the heat transfer responses are tabulated in the form of graphs and furnished in the form of graphs, and by reading the graphs you can measure the temperature of your actual case. So వాటిని Heisler and graphical solutions అంటారు, Heisler and Grover charts అంటాం. Heisler charts ఎప్పుడు ఇస్తారు, ఎప్పుడు వాడతారు అనేది just refer to any text. Okay, the answer is D for that. Now assertion and reason entered. Okay, during the temperature measurement of hot gas in a duct that has relatively cool walls, the temperature indicated by the thermometer will be lower than true hot gas temperature. The thermometer ekkada undi, cool wall lo undi, hot gas emo veltundi. Okay, the sensing tip of the thermometer receives energy from the hot gas and loses heat to the duct. అంటే ఈ థర్మోకపుల్ partly exposed to the duct and partly exposed to the fluid. A hot fluid అది సెన్స్ చేస్తూనే it tries to reach the temperature of the fluid, but at the same time duct కూడా కాంటాక్ట్ ఉంది కాబట్టి it gives away heat to the duct, and therefore thermocouple measure చేసే టెంపరేచర్ erratic గా ఉంటుంది. ఓకే, సో ఇది ఓకే, సో వాట్ ఈస్ ది ఆన్సర్ అనేది మనకు both A and R individually, assertion and reason are individually correct. Okay, normally thermocouples are embedded at the walls. Now some of the temperature is given to the walls. Okay, right. Which of the following statements is correct? The curve for unsteady state cooling and heating of the bodies. ఇందాక మనం డిస్కస్ చేసుకున్నాం కదా, టెంపరేచర్ వేరియేషన్ విత్ టైం ఎట్లా ఉంటుంది. Is it a parabolic curve? Is it an exponential curve? And ఇక్కడ exponential curve asymptotic to the time axis. Time ఎక్కడ తీసుకున్నాం మనం ఇందాక కర్వ్ లో? X axis లో తీసుకున్నాం. టెంపరేచర్ ఎక్కడ తీసుకున్నాం? Y axis లో తీసుకున్నాం. So is it exponential only to asymptotic only to the x-axis or to the y-axis? మీరు ఇందాక చూస్తుంటే నేను ఆ టెంపరేచర్ ప్రొఫైల్ తీసేటప్పుడు TA ఇక్కడే పెట్టాను, అంటే ఇట్స్ రీచింగ్ y-axis. ఇక్కడ నుంచి ఇట్ ఇస్ డిక్రీజింగ్. So it is only asymptotic to x-axis, not to the y-axis. Okay, it can intersect y-axis. It can reach y-axis. Okay. So parabolic kaadu, hyperbolic kaadu, because t minus t infinity divided by ti minus t infinity is e to the power of something minus something. So that is an exponential curve only. So exponential asymptotic to time axis. So obviously answer is B. In a lumped heat capacity system, the temperature gradient within the system is negligible. In the analysis of lumped heat capacity systems, the thermal conductivity of the system material is considered very high irrespective of the size of the system. So దీంట్లో ఈ రెండిట్లో ఏది కరెక్ట్? లంప్డ్ హీట్ కెపాసిటీ సిస్టమ్ ఎప్పుడు వాడతాము? బయాట్ నెంబర్ ఈస్ వెరీ లెస్ అన్నప్పుడు 0.1 అనుకున్నాం కదా. సో వెరీ లెస్ ఎప్పుడు ఉంటుంది? కండక్షన్ రెసిస్టెన్స్ ఈజ్ లెస్ ఉన్నప్పుడు. కండక్షన్ రెసిస్టెన్స్ లెస్ ఉంటే ఏమవుతుంది? టెంపరేచర్ గ్రేడియంట్ విత్ ఇన్ ద సిస్టమ్ ఇస్ నెగ్లిజిబుల్. అంటే టెంపరేచర్ గ్రేడియంట్ ఆల్మోస్ట్ హారిజాంటల్ గా ఉండిపోతుంది. ఓకే, ది స్లోప్ గురించి మాట్లాడుతున్నాడు. ఇది ఎప్పుడు ఈ హారిజాంటల్ లైన్ r is equal to 0 అన్నప్పుడు మనం డిస్కస్ చేసుకున్నాం కదా. సో నెగ్లిజిబుల్ రెసిస్టెన్స్ ఉన్నప్పుడు టెంపరేచర్ గ్రేడియంట్ తక్కువగా ఉంటుంది. ఓకే, సో దట్ ఈస్ ఫస్ట్ స్టేట్మెంట్ ఇస్ కరెక్ట్, అసర్షన్ ఇస్ కరెక్ట్. రీజన్ ఏంటంటే అనాలిసిస్ ఆఫ్ లంప్డ్ హీట్ సిస్టమ్ థర్మల్ కండక్టివిటీ సిస్టమ్ మెటీరియల్ ఇస్ కన్సిడర్డ్ వెరీ హై. థర్మల్ కండక్టివిటీ హై ఉంటేనే కదా రెసిస్టెన్స్ నెగ్లిజిబుల్ గా ఉండేది. సో రెండు కూడా ఓకే. సో ఇంకోటి కూడా అడుగుతాడు లంప్డ్ బాడీలో. లంప్డ్ కెపాసిటీ అనాలిసిస్ ఆఫ్ అన్స్టడీ స్టేట్ హీట్ కండక్షన్ అజ్యూమ్స్ a constant uniform temperature throughout a solid. ఓకే, మనం ముందే అనుకున్నాం కదా, అది కరెక్టే. ఎందుకంటే we said the entire mass of the entire body will be at the same temperature, then only we call it lumped body. There cannot be any temperature variations within the lumped body. That's what it is saying. The surface convection resistance is very large compared to internal conduction resistance. Mali you go to the Bayard number, conduction resistance to convection resistance. Surface resistance and convection resistance. అది చాలా ఎక్కువ ఉంటుంది. ఇంటర్నల్ కండక్షన్ రెసిస్టెన్స్ చాలా తక్కువ ఉంటుంది కాబట్టి Bayard number తక్కువ ఉంది. రెండు కరెక్ట్. అసర్షన్, రీజనింగ్ రెండు కరెక్ట్. ఓకే, సో ఇక్కడ ఎవరో క్రిటికల్ రేడియస్ గురించి అడిగారు కాబట్టి మళ్ళీ వాళ్ళకు ఐఎమ్ జస్ట్ లివింగ్ ఇట్. అప్ టు ది క్రిటికల్ రేడియస్ ఆఫ్ ఇన్సులేషన్, added insulation increases the heat loss, added insulation decreases the heat loss, convection heat loss is less than conduction heat loss, heat flux is decreased. So what do we say? Up to the critical radius of insulation, heat loss increases. అంతే కదా, simple. సో R is equal to 0 అంటే ఇన్సులేషన్ రేడియస్ లేదు, ఇన్సులేషన్ బేర్ పైప్. ఇక్కడ నుంచి అప్ టు క్రిటికల్ రేడియస్ ఆఫ్ ఇన్సులేషన్ ఇక్కడి వరకు, when R is equal to బేర్ వైర్ నుంచి క్రిటికల్ రేడియస్ ఆఫ్ ఇన్సులేషన్ వరకు, what is happening to the heat transfer? Heat transfer is increasing. Okay. Copper radius of 0.5 mm is a wire of radius, copper wire of radius 0.5 mm is insulated with a sheathing of thickness 1 mm having a thermal conductivity of 0.5 watts per meter Kelvin. అంటే ఏంటి, ఒక ఇన్సులేషన్ 1 mm 0.5 రేడియస్ పైన 1 mm థిక్నెస్ అంటే ఏంటి, అవుటర్ రేడియస్ ఎంత వస్తుంది ఇన్సులేషన్ కి 1.5 mm అవుతుంది. ఎందుకంటే థిక్నెస్ 1 mm దాని రేడియస్ 0.5 mm. పిక్చర్ లో గీయాలా అవసరం లేదంట. కాపర్ వైర్ ఇది 0.5 అండ్ దీని మీద ఇన్సులేషన్ ఎంత థిక్ ఉంది, ఇది థిక్నెస్ గురించి రాస్తాడు. ఈ థిక్నెస్ మాత్రం 1 mm ఉంది అంటాడు. అంటే అప్పుడు రేడియస్ ఎంత కావాలా, 1.5 mm. ఎందుకు, ఈ థిక్నెస్ 1 మీటర్, ఈ రేడియస్ 0.5 మీటర్, 1. So the insulating thermal conductivity in picture. Outside heat transfer coefficient is 10 watts. Okay, that's fine. Now if the thickness of insulation of sheathing is raised by 10 mm, అంటే raised by అంటే ఆల్రెడీ 1 mm ఉంది, ఇంకో 10 mm యాడ్ చేస్తున్నాం అంటే అప్పుడు ఏమైంది, థిక్నెస్ అలోన్ ఈ థిక్నెస్ అలోన్ ఈజ్ 11 mm. ఓకే, దిస్ ఈజ్ 0.5. సాలిడ్ గురించి మార్చలేదు 0.5. సో ఇదేమైంది, ఆర్ ఇస్ ఈక్వల్ టు అవుటర్ రేడియస్ R2 ఇస్ ఈక్వల్ టు 11.5 mm. ఓకే, ఒక దాంట్లో ఏమో 1.5 mm అవుటర్ రేడియస్ ఉంది R2, ఇంకో దాంట్లో R2 డాష్ ఏమవుతుంది 11.5 mm R2 డాష్. ఓకే, సో same insulation material. Now, then the electric current capacity of the wire will be, అంటే హీట్ ట్రాన్స్ఫర్ పెరుగుతుందా తగ్గుతుందా అనేది ఇష్యూ అనమాట. దీనికి వెరీ సింపుల్, మీరు ఇప్పుడు K by H క్యాలిక్యులేట్ చేయండి. వాట్ ఇస్ K? 0.5. H ఎంత, 10 అంటే 0.05 మీటర్స్ అవుతుంది. 0.05 మీటర్స్ అంటే ఎంత అవుతుంది, 5 mm వరకు అవుతుంది. క్రిటికల్ రేడియస్ ఎంత అయింది, క్రిటికల్ రేడియస్ 0.05 కదా, అంటే 5 సెంటీమీటర్స్ అవుతుంది. ఇక్కడ మీకు ఎంత ఉంది, 11.5 మాత్రమే ఉంది. అంటే ఏంటి, ఇంకా క్రిటికల్ రేడియస్ రాలేదు. అంటే ఏంటి, ఇంకా హీట్ ట్రాన్స్ఫర్ డిక్రీజ్ అవుతూ ఉంది, ఇంక్రీజ్ అవుతూ ఉంది. అంటే బేర్ వైర్ నుంచి మీరు ఎంతవరకు 5 centimeters అంటే 50 mm వరకు కూడా మీరు యూ కెన్ గో ఆన్ యాడింగ్ ఇన్సులేషన్ అప్ టు క్రిటికల్ రేడియస్. 5 centimeters వేస్తే నీ క్రిటికల్ రేడియస్ వస్తుంది. నీ రేడియస్ ఎంత ఉంది, అవుటర్ రేడియస్ 11.5 అంటే ఏంటి, ఇట్ హస్ నాట్ ఎట్ రీచ్ ద క్రిటికల్ రేడియస్. దట్ మీన్స్ వాట్, హీట్ ట్రాన్స్ఫర్ ఇస్ ఇంక్రీజ్. When heat transfer is increasing, resistance is decreased and the capacity of the wire to carry heat will be increased. Okay. Copper, okay, this one. In the current carrying conductors, if the radius of the conductor is less than the critical radius, then addition of electric insulation is desirable. Okay, ఇప్పుడు ఏమంటాడు, కరెంట్ క్యారింగ్ కండక్టర్ ఉంది, రేడియస్ ఆఫ్ ద కండక్టర్ అంటే ది అవుటర్ రేడియస్ ఆఫ్ ద కండక్టర్ ఈజ్ లెస్ దాన్ క్రిటికల్ రేడియస్ అయినప్పుడు యూ కెన్ గో ఆన్. ఎలక్ట్రిక్ క్యారింగ్ కండక్టర్స్ లో వాట్ డిడ్ ఐ సే, the very purpose of insulating the electric carrying conductor is to enhance the heat transfer. To electric carrying conductor insulation, till what point you can use, you can go up to the critical radius of insulation, right? So if it is less than the critical radius of insulation, the bare wire, you can go on adding insulation up to critical radius and still you can enhance the heat transfer, right? It reduces the heat loss. Adding insulation, if it is less than critical radius, adding up to critical radius, ఏమవుతుంది, it reduces the heat loss from the conductor? No. It increases the heat loss from the conductor and thereby enables the conductor to carry heat. That's right. ఎందుకంటే bare wire, please listen, bare wire radius is less than critical radius. You add insulation until you reach critical radius, heat transfer increases. So that's what I said. Addition of insulation to the outside surface of a pipe always reduces heat transfer rate, and a critical radius concept has no significance. Addition of insulation to the inside surface of a pipe. Like at the beginning, your question so same thing. Inside of the pipe is say now critical radius of concept as a that's true. And if insulation is added to the inside surface, both surface and internal resistance increases. That would not chip. So both A and R are individually true. Okay. Electric cable of aluminum conductor K is to be insulated with rubber. Okay. Rubber insulation. ఇక్కడ మళ్ళీ చూడండి రెండు థర్మల్ కండక్టివిటీస్ ఇస్తున్నాడు. నేను ఎప్పుడు ఏం చెప్పాను, when you are talking about critical radius of insulation, you talk about only insulating material thermal conductivity. The cable is to be located in air, 6 watts per meter square undala, M2 and the critical thickness of insulation will be K by H. అంటే ఇక్కడ 240 is given to confuse you. Aluminum conductor thermal conductivity we don't use. We talk about only two resistances: insulation conduction resistance and the convection resistance. So therefore, it is 0.15 divided by 6. So, ఎంత వస్తుందో మీరు క్యాల్కులేట్ చేసుకోండి. So it is 25 అనుకుంటా. 25. Consider the following statements. Under certain conditions, an increase in thickness of insulation may increase the heat loss from a heated pipe. Yes, critical radius work increase avutundi. The heat loss from an insulated pipe reaches a maximum when the outside radius of insulation equal to the ratio of thermal conductivity to surface constant, K by H. K by H enti critical radius. Yes, small diameter tubes are invariably insulated. Okay. Not necessary. Economic insulation is based on minimum heat loss from the tube. Not necessary. Economics is something else. Economic analysis setlundi. How much of heat loss you are stopping and how much you are gaining by stopping the heat loss in terms of money. Because heating requires electricity, let me say. It consumes electricity. Some heat is unnecessarily lost. That means you are consuming electricity straight away. So it is accounting to money, and to prevent the heat loss, you are purchasing insulation. So insulation cost entundi. Initial investment entundi, ento saving vastundi. So dani base cheskoni economic insulation gurinchi maatladtam gaani ee technicalities base cheskoni manam maatladam. So economic insulation depends on the insulation cost and the energy cost, all this cost. So 1 and 2 are correct. 1 and 2 are correct. Small diameter tubes are invariably insulated. No, there is no such necessity. Who said all small tubes are to be insulated? Okay. Steel pipe is to be lined with 2 layers of insulating materials of different thermal conductivities. Okay, ఇది మనం already discuss చేసుకున్నాం. Steam pipe is to be lined with 2 layers of insulating materials of different thermal conductivities. And 2 insulating materials. If you recollect that problem on a slab, K unna oka insulating material, 2K unna inko insulating material. Edi first cheyali, edi second cheyali. Annadani manam discuss chesthe manam em anukunnam, K unnadani first cheyali, 2K unnadani second cheyali, then heat transfer will be less ani anukunnam, right? So better insulation must be put inside. Straight away answer is that. Okay. Now a long cylinder rod. The last problem before we take a 5 minutes break. In a long cylindrical rod of radius R and a surface heat flux of Q naught, the uniform internal generation rate is. There is a cylinder and heat flux on the surface of the cylinder is happening to a quantity of Q dot. Heat flux on the surface and what is heat flux? Heat transfer rate per unit area. Am I right? Heat transfer rate per unit area. Yeah. Wrong sir. The 2Q dot by R. Indaka calculate chesam kada? A should be the correct answer. Temperature variation in a large plate as shown in the given figure would correspond to which of the following conditions. I'll leave it to you because ఈ ఫిగర్ కాన్కేవ్ డౌన్వర్డ్స్, కాన్కేవ్ అప్వర్డ్స్ అండ్ లీనియర్ వేరియేషన్ నేను ఇచ్చాను. సో it is only steady state with variation of k. K is equal to k naught into 1 plus alpha. Okay, so 1 plus beta t. So దాంట్లో the B2 is the correct answer. I'm just leaving it here. Take 5 minutes break, please. When we come back, few more gate questions and straight away I start convection heat transfer. Thank you. So, welcome back. So, if you remember, I have drawn this temperature profile. So, when is it happening? So, it's wet. Please recollect this diagram I have given. For all beta positive, oops. For all beta positive, and a straight line is when beta is equal to 0, and this is beta is negative. So what is beta? I said k is equal to k naught into 1, k naught into 1 plus beta t. Okay, so that's how we have discussed, and therefore he has given only this profile to you, and straight away you can relate to that. So a few questions on what is this extended surfaces, pins. From a metallic wall at 100 degrees centigrade, a metallic rod protrudes from the ambient to the ambient air. The temperature at the tip will be minimum when the rod is made of. Okay, there is a base onto which a metallic rod is rod is protruded. The tip temperature, when is it going to be minimum? When which kind of material is used? It doesn't require much of an investigation. You need to know the thermal conductivities, because if fin has very high thermal conductivity, the entire fin will be at the same temperature of the base, meaning even at the tip it will be the temperature of the base. When the thermal conductivity is very high, when the thermal conductivity is very high. When thermal conductivity is low, when it decreases, definitely gradient increases. So therefore, lower thermal conductivity material among all the four, will have minimum temperature at the tip. So silver has highest thermal conductivity, copper, then aluminum, and steel among all the four will have lower thermal conductivity. So therefore, when you use steel, the tip temperature will be less. On a heat transfer surface, fins are provided. Why fins are provided? I don't answer this. Increase temperature gradient so as to enhance heat transfer. To increase turbulence in flow for enhanced heat transfer. To increase surface area to promote the rate of heat transfer. To decrease the pressure drop of the fluid. Forget about all that. The very logic I have used is Q is equal to HA delta T. When you don't have control over H and delta T, the only way you can increase the heat transfer is by enhancing the surface area. So, increase the surface area undala or surface area. Okay. Insulated tip temperature of a rectangular longitudinal fin having an excess over ambient root temperature of theta naught. అంటే ఇందాక base temperature theta b అనుకున్నాం కదా. Now it is theta naught, he says. What will it be? Okay. So what is it? Tan HML by ML kada. Insulated tip temperature distribution, when temperature distribution equation. Theta by theta naught is equal to tan HML by ML. Theta naught యువతలు తీసుకొస్తే theta naught tan HML by ML. Oops. Where is it? A tip temperature. I'm sorry. So I'm really sorry. I gave you wrong. Yeah. I'm really sorry for the confusion. tip insulated temperature, this is very long, infinitely long. Yeah, here it is. So the temperature distribution equation for a tip insulated condition is T minus T infinity divided by TB minus T infinity is equal to cos Hm into L minus X divided by cos Hm. Now, where is he asking the temperature at the tip? Please remember, this is the temperature distribution equation for a tip insulated condition. So this is theta naught, whatever you say, TB minus T infinity theta naught. Where are you measuring the temperature? At X equal to L. L minus L is 0, cos H of 0 is 1, and therefore it is 1 by cos HML. It's 1 by cos HML. So theta naught into theta naught ఇటువైపుకి వచ్చేస్తుంది. So theta naught divided by cos HML is the answer. I'm sorry, I picked up a wrong equation. This is the fin efficiency equation, not the temperature distribution equation. So D is the correct answer. The efficiency of a pin fin with insulated tip. ఇందాక నేను కన్ఫ్యూజ్ అయిన ఈక్వేషన్ మళ్ళీ వచ్చింది. So the pin fin with insulated tip efficiency equation is tan HML by ML. We have discussed that. Fin length of L protrudes from a surface held at a temperature greater than the ambient temperature TA. The heat dissipation from free end of the fin is assumed to be negligible. And the tip is insulated. Tip is insulated. The temperature gradient at the fin tip dt by dx. We all know at an insulated condition dt by dx is 0. Simple. So need not get confused. The heat dissipation from the free end of the fin is assumed to be negligible. So it is insulated. Usually fins are provided to increase the rate of heat transfer, but fins also act as insulation. Which one of the following non-dimensional number decides this factor? So, ఈ numbers అన్నిట్లో కూడా we already know bad number and Fourier number. Fourier number is all about heat stored and heat transmitted. Bad number talks about the conduction resistance to convection resistance. So, what is the resistance happening within the fin material? What is the convection resistance? What is the relevant number, non-dimensional number is Bayes number. But unlike lumped heat capacity bodies, the Bayes number need not be low. Bayes number can be equal to 1. It has an equal amount of conduction resistance and convection resistance. So there are two things. When you are analyzing a fin, what is the resistance for the heat transfer by conduction through the fin? And what is the resistance offered for convection? So Bayes number represents an appropriate one. Provision of fins on a given heat transfer surface will be more if there are fewer number of thick fins. ఏది కావాలి మనకి? Do you need less number of very thick fins, fewer number of thin fins, large number of thin fins, large number of thick fins? See, if fin thickness will only add weight to it and it will not enhance the surface area. Again, let me tell you, if you have any doubt on that, I'm sorry, I should be drawing a 3-dimensional view of it. Okay. Let me talk about a fin. Now, this is the thickness I am talking about. Thickness, this thickness. If this thickness is enhanced, you are adding only this area. Whatever, if you enhance the thickness, you are adding only this area. Instead, what you can do, you can halve this and you can add 2 fins. Now, what happens when you are adding and halving and adding 2 fins? T by 2 fins చేసామనుకోండి, ఇక్కడ ఒకటి, ఇక్కడ ఒకటి. Okay, సో ఇదే థిక్నెస్ లో సగం సగం పెట్టామనుకోండి, సర్ఫేస్ ఏరియా ఎంత ఎక్కువ పెరుగుతుందో చూడండి. అల్టిమేట్లీ ది కాన్సెప్ట్ ఈస్ టు ఇంక్రీజ్ ది ఏరియా. సో whenever fins, you don't refer to very thick fins. Thick fins will not help you. Thin fins, because major surface area comes here on the top and at the bottom. So thin fins are preferred. More number of thin fins is advantageous to you. So large number of thin fins are preferred. Which one of the following is correct? Fins are used to increase the heat transfer from surface by increasing the temperature difference, increasing the effective surface area. Now it's anyone's guess. Consider the following statements pertaining to large heat transfer rate using fins. Fins should be used on one side, on the side where heat transfer coefficient is small. Okay. Long and thick fins should be used. No, I simply said thick fins cannot be used. So 2 is ruled out. 2 it is ruled out straight away. Long and thick fins shall not be used because it unnecessarily adds weight. It is not helping you with the heat transfer surface area. Short and thin fins should be used. Yes, thermal conductivity of fin material should be large. So K should be large. We all know that K should be large. I just gave you one aspect. Natural convection లో efficiency ఎక్కువ ఉంటుందా, forced convection లో efficiency ఎక్కువ ఉంటుందా? So tan HML by ML అనే కండిషన్ తీసుకొని I just explained it to you that natural convection లో efficiency is very high. So 1, 3 and 4 should be good. In a liquid to gas heat exchanger, fins are provided in the gas side. అంటే for example, automobile radiator. Radiator upper header receives hot water. The water dribbles down the pipes connected vertically in the radiator, and air moves on the outer surface. And fins, number of fins, that is the matrix you see in the radiator. Number of fins, parallel fins are placed. Now, is it advisable to place fins on the liquid side or within the pipe or outside? Normally, we face the fins on the gas side because gas heat transfer coefficient, the gas can easily flow between the fins. So, that is correct. The gas offers less thermal resistance than the liquid. This is irrelevant. This is irrelevant. I think A is true, but R is the gas offers less thermal resistance than liquid. Maybe I will just get back to you. Maybe it's not very clear. Please remind me tomorrow. I'll explain this. I'm sorry. Nusselt's number is always greater than unity. Nusselt's number, let us not discuss because it comes in convection heat transfer. Consider the following statements pertaining to heat transfer through fins. Fins are equally effective irrespective of whether they are on the hot side or cold side of the fluid. No, fins are effective on the cold side of the fluid, hot side of the fluid. Temperatures along the fin is variable and hence the rate of heat transfer varies along the element of the fin. Yes, along the length of the fin, temperatures vary. The fins may be made of materials that have higher thermal conductivity than materials of the wall. Yes, that is preferred. Fins must be arranged at right angles to the direction of flow. No, no. So the last one is also not no. No. This is correct. Okay. So what is answered? 2 and 3 are correct. Fins are effectively, I told you, fins are effectively effective irrespective of whether they are on the hot side or cold side. Because when they are on hot side, temperature gradient can be maintained, that heat transfer can be effective. And initially, the fundamental aspect of the fin heat transfer is initial convection should happen into the fin, and thereafter convection heat transfer into the ambient conditions, right? So therefore, first is also ruled out, and right angles, why it is not true, I'll tell you. the fluid is flowing, the fin should be parallel to the fluid flow direction. Now what happens if fin is placed, maybe let me say a fin is placed and the fluid is moving in this direction. If it is right angle, the other side of the fin, one side of the fin is exposed to fluid, other side of the fin is deprived of the fluid flow. In order to achieve maximum heat dissipation, the fin should be designed in such a way that it should have a maximum lateral surface at the root side of the fin. It should have maximum lateral surface towards the tip side of the fin. It should have maximum lateral surface near the center of the fin. It should have minimum lateral surface near the center of the fin. Okay. Now, let me see. Lateral surface and the circumference. He is talking about the circumference of the fin. So, there's one fin. At the base of the fin, lateral surface is higher. This is one thing. The second thing he says is the fin has minimum area at the base and maximum area at the tip. And the third case he is talking about, I think I understood it properly. Okay. He is talking about maximum lateral surface at the center. And in the fourth one, he is talking about a fin with a minimum lateral surface at the center. Now, in any case, I prefer the first one because any heat that is entering the fin enters at the base. So the cross-sectional area where it is attached to the base should be higher. If this is the case, minimum area at the base, minimum amount of heat transfer enters into the fin. Because it's equal to Q is equal to minus Ka dt divided by dx, right? If A is small at the base, minimum amount of heat transfer takes place. So entire heat transfer of the fin is disturbed. Now, even this case, the heat transfer after this will be effective only up to the center, and at the center area is reduced, and therefore heat leaving the center will be minimum. Even that is not. And there's no point in adding higher cross-sectional area because when lateral area is high, cross-sectional area is also high. No point in adding cross-sectional area at the middle, whereas the cross-sectional area should be at the beginning, at where the fin is joined to its base, and therefore higher lateral surface or higher cross-sectional area is preferred for a fin at the base. So A is the answer. Should have maximum lateral surface at the root side of the fin. Okay, root, tip, center. That's what it says. So some of these questions and short questions we have answered. Now we have another 20 minutes. Let me introduce convection to you. Here I just stop for a minute and request all my student friends there. With this, in the limited time available, I thought I could discuss important concepts of conduction heat transfer. And any generic question, any question that you are problem that you are facing a problem, you can just transfer it to me through mail, probably. I'll take some time, maybe give me a couple of days time to answer your questions. I'll answer. Okay. So feel free, but please understand, I have only a limited time. Explaining a subject like heat transfer, which is mathematical oriented, which involves a lot of derivations, which requires a lot of writing on the blackboard kind of a thing and explaining the concepts. I'm just trying to explain it in 10 hours, right? Entire conduction heat transfer. Definitely, I have my limitations, and If you have any problem, please don't hesitate to contact. Now, the mechanism of convection heat transfer. I said convection heat transfer is all about advection or the bulk motion of the molecules. Molecules necessarily should go, the fluid particles necessarily should go to the hot spot, pick the heat, and go to the low temperature zone. So a continuous current of this shall be ensured. And in forced convection, you are using a device like this. In a forced convection, you are using an external gadget like a fan or a blower or a compressor or a turbulent generator, whatever. So you are blowing air over that, and therefore heat transfer takes place. In natural convection, this, of course, you can orient the direction of the fluid any way you wanted, because anyhow you are creating convection current or the fluid flow patterns the way you wanted. It can be a vortex flow, it can be a linear flow, it can be any kind of a flow that you can design, so that you can make the heat transfer effective. Ultimately, every molecule is coming, every fluid particle is coming and touching the plate, acquiring the heat and going. Now, in natural convection, the warmer air should raise upwards. And that's what I said about buoyancy force. Now, how do you establish this? It's summer anyhow. If it is not an air-conditioned room, in the midday, you go to your room, enter into your room, switch on the fan, and stand right below the fan. Make sure that the fan is properly installed. Right, stand right below the fan. You see hot air is blown onto your head. Where is this hot air coming from? As you enter into the room, you did not notice such a high temperature. Whereas once you switch on the fan, hot air starts blowing onto your head. Now, where is this hot air coming from? All through the day, because temperatures are soaring, the heated molecules being lighter, they all go and settle near the roof. And at the floor, because the roof also receives radiation, right, directly from the sun, and therefore it is a high temperature zone. And the floor is not directly exposed to the radiation, so floor is at relatively lower temperature. So colder molecules naturally settle down, and heated molecules go up. So all the heated molecules settle at the top, and when you switch on the blower, now I think you must have studied about thermosiphon cooling system also for the IC engines. Where water circulates on its own without a pump. Hot water moves up and cold water comes down. So this is the mechanism by which you circulate the fluid flow. Now, in the room, colder molecules will always settle down and hotter molecules will go. That is the reason why. And today, of course, when with the air conditioners in your rooms, we are not providing those ventilators on top of the room. So why ventilator is provided at the top of the room? The hot air can escape through. So hot air vertically moves up into the towards the roof of the room, and when you provide a ventilator right on the top corner, so you are paving way for the hot air to move out, escape, and therefore you are creating lesser temperatures. So that is the people, I don't know whether they have studied natural convection or not, but with their practical exposure they have created those things. So natural convection is all about heated air moving up, colder air coming down. I think I have given you the best example. The deep freezer in a refrigerator always kept at the top. So convection is also possible when there are no convection currents, and also when convection currents cannot be possible. The same example that I have given: bucket of water heated only halfway through, all heated water will be on top because they are lighter in weight, and the colder molecules of water, where the heat has not affected the temperature, so they will settle at the bottom. So when there is no convection current, only possibility is conduction between the fluids because of the collision happening between the fluids. So this is what I just wanted to tell you. Fluid motion enhances the heat transfer since it brings warmer and cooler chunks of fluid into contact, initiating higher rates of conduction at a greater number of sites in the fluid. Okay, so the fluid motion is the key for the heat transfer in a convection heat transfer. How quick? Now, again, when you are talking about the same principle, there are a number of parameters which are controlling the fluid motion, particularly in natural convection. In forced convection, of course, you are using an external device, you are creating that pressure drop, and therefore you are forcing the fluid to flow. And you can decide the velocity at which the fluid should flow in a forced convection condition. In natural convection, the convection currents are basically because of the buoyancy effects, temperature gradients. The heated molecule should go up and colder molecule should come down. And again, this is controlled by various parameters. For example, viscosity. Now I have air in the room, and you have viscous fluids in the room, like castor oil or lubricating oils, etc. Even if the lubricating oil becomes heated up, it loses its density, but then it wanted to flow up. When it flows up, there are innumerable number of molecules. I think Avogadro number talks about the number of molecules in unit space, right? So, innumerable number of molecules. The lighter molecule always tries to vertically move up, but the viscosity. What is viscosity? Viscosity is the resistance to flow. Now, the viscosity is a property of the fluid. The resistance offered by the fluid for this molecule to float up, when it is higher than the buoyancy force, the driving force which is causing it to move up, quite obviously, even a lighter particle cannot move up so easily. So viscosity plays a very, very dominant role in natural convection. Even in forced convection it plays, but a very dominant role it plays in natural convection principles. Because the fluid particle movement, vertical upward movement of the fluid particle, the heated molecule, shall be very freely happening, and this happens when viscosity is very less. Opposing or resistance to the forward upward movement is less for the molecule. The second thing is, you will be surprised, we did discuss about the specific heat. What is specific heat? Specific heat is the amount of heat required to raise the temperature of unit mass of a substance. So, a fluid with lower specific heat means you add lesser amount of heat to it, its temperature increases considerably. In contrary, when the fluid has higher specific heat, you add the same amount of heat as you have added to the earlier fluid with lower specific heat. This fluid with higher specific heat, its temperature will not increase considerably. When temperature is not increased considerably, quite naturally, the buoyancy forces will be minimum, because density is a function of temperature. See, I added 20 watts to this fluid, its temperature increases by say 5 degrees centigrade, so it is very quickly moving up because temperature is considerable. I added 20 watts to another fluid, its temperature has increased by only 1 degree centigrade. Its density is not increased as much, and therefore buoyancy force experience is various. Again, density as a function of temperature. Some of the fluids lose their density with temperature very easily. Some of the fluids, the density variation is not much with variation in temperature. So density is another factor that controls the natural convection. See, ultimately, forget about rest of the things. Convection heat transfer is all about the convection currents created, bulk motion of the fluid molecule. If there are opposing forces to the natural motion of the fluid, particularly in natural convection heat transfer coefficient will be very, very less, or convection heat transfers will be less. And such fluids where with minimum resistance, with all favorable conditions like low specific heat, density decreases very readily with the temperature, and viscosity is very low. These molecules, such fluids, they rigorously participate in convection heat transfer. The rates of convection heat transfer is also very, very high. Heat transfer between two parallel fluids is the case that is given here. So, Newton's law of cooling, I need not talk to you. Here, once again, I talk about heat flux and heat transfer. Heat flux is per unit area. A is missing here in this equation, and A is taken out of the side. Capital Q becomes small q, because small q is capital Q by area. So just now I was explaining to you, heat transfer strongly depends on fluid properties like viscosity, thermal conductivity, density, specific heat, as well as fluid velocity. Now, what is thermal conductivity? Thermal conductivity, the fluid is going and coming in physical contact with the hot spot. Now, there is a physical contact between the fluid molecule and the solid surface. Unless otherwise radiation is coming into play, unless otherwise the fluid particle receives the energy through radiation mode of heat transfer, the fluid molecule necessarily has to go sit on the top of the hot spot and conduct heat. Now, there is a physical contact, heat transfer is by thermal conduction. So, if the material has higher thermal conductivity, it receives more heat from the hot body, the molecule receives more heat, and it becomes lighter, its temperature increases. Whereas, otherwise, if the fluid molecule has lower temperature, lower thermal conductivity, even on physical contact with the hot plate, the heat acquired by it is less, heat transferred to the molecule is less, and therefore its temperature will not go. And also depends on the geometry, because these molecules will be sliding on the surface. When it is a rough surface, the heterogeneous friction between the wall and the fluid particles will be very, very high. When the friction is high, the fluid movement on the solid surface is greatly restricted. So again, the roughness and the geometry of the solid boundary also comes into picture when we talk about convection heat transfer. That's what I said. Unlike conduction heat transfer, where thermal conductivity is only a property of a material, and you pick up a material, how much is the conduction capability of the material is readily known from the data books. Whereas here, it depends on number of other parameters. You need to analyze each parameter and its influence on convection heat transfer. Ultimately, the rule is that the molecule should come to the hot spot, acquire the heat, and go up. And this should continuously happen. And the convective heat transfer coefficient, rate of heat transfer between solid surface and fluid per unit surface area per unit temperature difference. That's how you define. H is what? When you make A is equal to 1, delta T is equal to 1, I say H into 1 into 1 is equal to Q. That means what? It is the heat transfer rate when unit surface area participates in convection heat transfer, and when temperature difference between the fluid and the solid boundary, or between the two interacting fluids, is 1 degree centigrade. Now, what happens? No slip condition means what? And a boundary layer means what? Viscosity effects we'll discuss. Right? Now, the velocity with which the fluid is coming, approaching the plate. Now, let me say the fluid here has not reached the solid domain, solid boundary. It is just approaching the solid, and this velocity, because it is not influenced by the solid, the presence of the solid greatly did not disturb the fluid motion, because the fluid has not reached the region of the solid. So this velocity, I call it as approach velocity or free stream velocity. And this will be uniform. It is not disturbed. When once it enters into the solid domain, a lot of things happen. And particularly in the immediate vicinity of the solid surface, the velocities keep changing. And what happens? The viscosity comes into picture. I was talking to you about heterogeneous friction the wall friction, what we normally call it, at the solid boundary, the friction will be enormous for the fluid molecule, and therefore fluid molecule which is moving at a free stream or approach velocity of v comes to a grinding halt when it touches the solid surface. Now, maybe 2 minutes I'll take. This is the plate and fluid is moving. This velocity until it reaches, I call it as u infinity or free stream velocity or approach velocity. When once it reaches the solid boundary, fluid is with millions of molecules, right? So those molecules which come closer to the wall, they initially were the molecules were traveling at a speed of u infinity or v, whatever you call it. Now, because of the wall friction, the molecules come to a grinding halt onto the walls of the solid boundary, and because of the friction and viscosity also comes into picture. So they lose all their velocity and they settle down on the top of the surface. Now they are not moving. Hitherto, before reaching the solid surface, they were moving. They were moving with the same velocity, all molecules, but those molecules, by opportunity which have come in contact with the solid boundary, they stopped moving because of the wall friction. Because of the wall friction. Now, what happened? One layer of molecules, let me analyze it layer by layer. One layer of molecules settled down on the wall, and it is because of the wall friction that is encountered. Now, the second layer of molecules, now they are not coming in direct contact with the solid plate because already one layer of molecules have settled down and no slip condition, they are not moving, they are stagnant, and on top of it, these molecules they approach it with a velocity of v. Now, these molecules cannot come to zero speed, zero velocity, but they also experience enormous, great friction because the molecules are sitting pretty on the solid surface, the first layer, they are rubbing against the stationary molecules. It is as good as a gentleman who is running, suddenly he when rubs against a standing person, he loses all its momentum, isn't it? A running person comes and rubs against a standing person, he loses its momentum. So similarly, these molecules, upon coming in contact with the first layer of molecules, they also greatly lose their velocity, and but then they exhibit the tendency to move slightly forward with greatly reduced velocities. Here, the advantage of the second layer of molecule is they are not coming in direct contact with the solid surface. They are not coming in direct contact with the solid surface. Now, it is the friction between molecule and molecule. Only viscosity is coming into picture. And of course, the inertial effects are there. Because the earlier molecule, the inertia example that I gave, a man standing, another man came running and hit him, he will lose all his speed. So the inertial effects. So one is stationary, second one is rubbing against it, and therefore it also exhibits a tendency to lose all its energy. But these molecules are not experiencing as much friction as the earlier molecules experience, and therefore they start moving. Now the next layer of molecule, now they are rubbing against second layer of molecule. What is the nature of second layer of molecule? Second layer of molecules are already set on motion with minimum velocity. They are not like stagnant molecules of the first layer. And also, these third layer of molecules will not, like second layer of molecule, will not come across the wall friction. It is a little away from the wall. The wall friction effects are not greatly felt. So it is again rubbing between the two molecules, viscosity coming into picture, inertia coming into picture. But the only difference is this time it is rubbing against a molecule. I am sure the molecules will not be flowing layer by layer like I am explaining, but still Let me explain the way I can explain the concept. So, this third layer of molecules are at a little more advantage, they can pick up the velocity. Similarly, the same explanation can be given layer after the layer, as you move away from the plate, the wall friction effects and the inertial effects are not felt, and finally there comes a point where the molecule will be moving at a free stream velocity. Because molecules before reaching the plate, they were moving at a free stream velocity, right? The same free stream velocity is regained by the molecule after a certain y distance. Well, let me say x is the direction of the fluid motion. Y is perpendicular to the plate, let me say. After certain delta y, you see after certain distance, the molecule is acquiring its free stream velocity, and thereafter every molecule will be moving at its free stream velocity. That means what this zone, it appears they are not in the influence of the wall friction and the presence of solid boundary. The viscous effects are overcome there, and therefore they continue to behave like as if there is no plate. But only after certain y distance, after certain distance from the plate. Okay, did you understand this? And that's what it is explained. Now look at these velocities, the relative velocities of the fluid layers. Layer by layer, you find initially it is zero velocity at the surface, and slightly increased velocity. Entire velocity is increased further increase, and then increase, and thereafter is a constant velocity of free stream V. So this is from here on, let me say that the effects of the wall boundary are not felt by the fluid. So there is one layer right on the top of the surface where the frictional effects are felt. We need to discuss about it a little in detail. So maybe I'll talk to you about remaining things because it's already 8. I should stop here. I just only said we started the case of a force of convection, and we did repeat what we have discussed about natural force of convection. Now, when force of convection is happening, now I said the frictional effects are coming into play and inertial effects are coming into play. The velocity loss patterns, I think I have explained it to you. We'll discuss more in detail. And friends, I have an small appeal to make to you, or information to give to you. Tomorrow being Sunday, I prefer to take the class between 3 p.m. and 5 p.m. Please bear with me. Tomorrow being Sunday, I would take this heat transfer class between 3 p.m. and 5 p.m. Please log on to, just like how you are viewing my lecture, please assemble at 3. Let's discuss about convection heat transfer. Thank you. Have a nice time. Bye.